Hello and welcome. In this video, we're going to talk about quadratic inequalities. We're going to talk about what they are, how to graph them and identify their solutions, how they can be used in an application sense, and how to solve a system of quadratic inequalities, both algebraically and graphically. Lastly, we're going to focus on how to write the equation of a quadratic inequality from a graph. So let's go ahead and jump right in. So we've been talking about quadratic equations for quite some time now, and we know that a quadratic equation, when graphed, forms a quadratic. We know that every xy coordinate is a point along that quadratic that lies on the curve. What we're going to be focusing on in this section is quadratic inequalities. So no more equal signs here, but we're going to be looking at less than or greater than, less than or equal to, greater than or equal to. And what that means is that we don't just have solutions that are points on a curve. We have solutions that are either inside or outside because we're describing the type of points or the type of ordered pairs that make a quadratic inequality true. So we're going to be looking for more of a range of answers, and that's going to lead us to talking about what this looks like graphically. So when we graph a quadratic inequality, this is going to give us a chance to just revisit how to graph quadratics in general. What we're going to do is temporarily pretend that we're looking at an equal sign. Temporarily pretend that we're graphing the quadratic function y equals whatever our function is. Then we're going to determine if our line or if the curve should be dashed or solid. So if it's an equal to, greater than or equal to, less than or equal to, our curve will have a solid line, or our curve will be solid. So when we have that or equal to, that's when we're going to be looking at something that's solid. When we just have less than or greater than, that's when we're going to be looking at a quadratic that is dashed or dotted. Then we're going to determine if we're supposed to shade above or below. So less than means that we should be shading below. Less than or equal to also means that we should be shading below the curve. Greater than means we should be shading above the curve. Greater than or equal to means that we should be shading above the curve as well. Then pick a test point, any point that's not on your quadratic. So most of the time that point we're going to pick is 0, 0, and you're going to determine if that statement is true or false. If it's true, then 0, 0 should be in the shaded region. If it's false, then 0, 0 should not be in the shaded region. So let's go ahead and practice. For number 1, I want you to pause the video, find the axis of symmetry and the vertex, and plot the points to sketch the curve. Then unpause the video and see how you did. So the opposite of b over 2a here is going to be -1, and if we plug -1 in to find our vertex, we get that y is 0 when x is -1. So our vertex is going to be the point -1, 0. Then there's no stretch or shrink. The only other transformation that's happening is that reflection. So we can graph the rest of the points using the parent function. From the vertex over 1 down 1, from the vertex over 2 down 4, from the vertex over 3 down 9. Now, before we connect the dots, we need to ask ourselves the question, is this going to be a solid or a dotted line? And that question leads us to our inequality. This is going to be a dotted line because there is no or equal to under the line, meaning the points along the curve are not included. So we're going to connect with a dashed or dotted line. Now we need to figure out where we're supposed to shade, if we're supposed to shade above the curve or below the curve. So less than means that we should shade under the curve. And I want to get it right up to the curve. And then I want to just test a point to make sure that I have shaded in the correct place. So I'm going to test the point 0, 0. 0, 0 is outside of where I have shaded. So when I plug it into the inequality, it should be false. Let's see what happens when I plug it in. 0 is less than 0 minus 1. This is false, so it should not be shaded, which it isn't, so we're right. So this blue graph is the solution, or is the quadratic inequality. And what that means is every ordered pair inside this shaded region, right, there's an infinite number, every ordered pair inside there is a solution to this quadratic inequality. All right, I'm gonna have you pause the video and try and work through graphing number 2 on your own, and then unpause the video and see how you did. So the axis of symmetry is gonna be x equals 1. When we plug that in to find the y value of the vertex, we're gonna get 5. So our vertex is at 1, 5. The only other transformation that's happening is this negative in front is telling us that we have a reflection across the y-axis. Sorry, we have a reflection across the x-axis, which means it's going to open downward. What I want you to notice is that I'm going to continue making points all the way until I get off of the graph. Because if I stopped at just these 5 points here, it's not going to be clear what's included in the shaded region and what's not included in the shaded region. So I want you to continue to graph points until they are all the way off of your graph. These bottom 2 you don't need, but it's going to help guide me when I'm connecting the dots. So this symbol, greater than or equal to, means when I connect, I'm going to have a solid line, a smooth curve, and then I need to decide if I'm shading inside or outside. So greater than or equal to means that I'm going to shade on the outside around the quadratic. And again, it should cover the whole area that we're shading right up to the curve. And then the last thing that we're going to do is we're going to test a point to make sure that we have graphed in the correct place. Again, I'm going to choose to test 0, 0 because 0, 0 is easy to plug in. Here, 0, 0 should not work. So let's see what happens if I test 0, 0. 0 is greater than or equal to 0 plus 0 plus 4. That's not true, which is what I wanted because it's not inside the shaded region. Okay, let's take this a little further and see a real life application of how this problem or how this type of problem could be used. So in a previous lesson, we talked about throwing your iPhone down the cliff at the Grand Canyon, and this problem is going to relate back to that example. So, do you remember the time you threw your iPhone down the cliff at the Grand Canyon? Your mom said you're grounded until you get back, so you decide to rappel down the cliff to retrieve your iPhone. The rope you use to rappel can support a weight in pounds as long as the weight, W, is less than or equal to 1,480 times d squared, where d is the diameter of the rope. So there's a relationship, which should make sense, between the diameter of the rope, how thick the rope is, and how much weight it can hold. We're being asked to graph the inequality and to interpret the solutions that we're graphing. So I'm going to start by making a table and setting up my graph. And since these numbers, if we're talking about the diameter here, these numbers are going to be pretty small. I'm going to space out my y-axis, and I'm going to have my y-axis be in thousands of pounds because 1,480, that's a really big number here. And we're going to be talking about small inches, like a half an inch, a third an inch. So I'm going to label my axes appropriately. So my y-axis, I'm going to have be weight in thousands of pounds. So this one means 1,000 pounds, 2,000 pounds, 3,000 pounds, 4,000 pounds, 5,000 pounds. And I skipped just so that I can space it out. I think it'll be easier to read and understand my graph that way. I'm going to make the x-axis, which is the diameter of the rope, which is in inches. I'm going to make every 2 lines a half of an inch. So now I have set up my graph. So in order to find some ordered pairs, we can't really use what we've been using on those past problems. We can identify, obviously, that the origin, or when there is no diameter, there is no weight. So to plot my points, I'm really going to be thinking about this as an equals sign, and then I'll deal with the inequality portion afterwards. So I'm going to put x, aka in this case the diameter, y, aka in this case the weight that it can hold. So if I plug in 0, I get 0. That's going to be my first point. If I plug in 1/2 squared is 1/4, and then I just need to do 1,480 divided by 4, which is going to be 370. So I'm just plugging these d values in here. If I plug 1 in, 1 squared is 1 times 1,480 is 1,480. If I plug in 3 over 2, that's going to give me 9 over 4. And then somewhere off to the side, we're going to multiply this by 9 and divide it by 4. On a problem like this where these numbers are so big, I don't have an issue with you reaching for a calculator just to make your life a little easier, but this is work that you could do by hand. If I plug in 2, I'm going to multiply 2 squared, 4, times 1,480. That's going to give me 5,920. And let's just get one more point. Let's get 5 halves. That's going to give me 25 over 4. And if I multiply that, I get 9,250. And that point's definitely not going to fit on my graph. So now I'm just going to do the best that I can to plot those points, the ones that will fit on my graph. And actually, the last 2 points don't fit on my graph. Now that I have these points, which it looks like half of a quadratic, which makes sense, I'm going to connect them with a solid line since it says or equal to, greater than or equal to. And then I'm going to determine where to shade. Less than means I'm going to shade below on my graph. And I know that I'm going to need to test a point just to make sure this makes sense, but it sort of automatically makes sense. We can't talk about it holding more weight than this, otherwise the rope would break. Contextually, I think that it only makes sense for it to be shaded below. But if we pick a different point to test, like 0, 1,000, that would be false. 1,000 is not less than or equal to that value. So we have shaded in the correct spot. So let's go ahead and interpret what this graph means. The graphed inequality is representing the weight that can be supported by the rope at various diameters. So if the diameter was 1.5 inches, it could hold any weight along here. So it could hold 1,000 pounds, it could hold 2,000 pounds, it could hold any point. So there are just an infinite number of points in here that are going to be true. So I'm going to go ahead and put that interpretation here for you to see. And there we have it. Now that we've looked at a problem in context, let's go ahead and take this a step further and talk about what we talked about in 3.5. What happens if we have more than one function at the same time? Graphing a system of quadratic inequalities is going to be really similar to how we graphed a system of quadratics and how we graphed linear inequalities back in Algebra 1. The idea is that we're no longer looking for where the two curves intersect, but where they're overlapping shaded regions, where their shaded regions are overlapping for each graph. That shaded area is going to be the solution that's going to hold all of the points that work for both quadratic inequalities. So let's look at this. We're going to start this process exactly the same. So I'm going to encourage you on number 4 to pause the video and just graph this first quadratic inequality on your own and then unpause the video and see how you did. So here we're going to have an axis of symmetry at x equals 0. It's going to open downward. The vertex is 0, 3. Less than is telling me that I'm going to shade inside because the inside is below this quadratic. And I could test 0, 0. 0 is less than 3, so it should be in the shaded region. Now go ahead and do the exact same thing if you have a different color with a different color for our second quadratic inequality. So this quadratic should be a solid quadratic, axis of symmetry, x equals -1, vertex -1, -4. Greater than means that I should be shading above. So now there is a region in which both of my shaded areas exist. This is why I like to use two different colors so it's a little easier to see. The solution to this quadratic system of inequalities is the overlapping region. So this purple area right here, this is my solution. And the graph is the solution in this case. You could identify a couple of points. 0, 0 is in here. 0, -1 is in here, -1, 0. All of the points within this shaded area where these two graphs overlap, this whole area is our solution. Now remember, a point on that dotted line or that dotted portion of the curve, that is not going to work. It has to be within this range. I'm going to encourage you to pause the video and work through number 5 all the way on your own and then unpause the video and see how you did. First curve, vertex 0, -4, shaded above because it's greater than, dotted curve. The next curve's not going to be so nice. That axis of symmetry is going to be 3/2. We're going to need to plug that in to find our vertex. So if I square 3/2, I'm going to get 9/4, and then that negative in front is going to keep it negative. 3 times 3/2 is 9/2 plus 4. I'm going to go ahead and convert that. 4 is 8/2. So this is going to be -9/4 plus 17/2. So common denominator is going to be 4. This is going to give me 17 times 2 is 34/4 minus 9/4. So 25/4. So not the nicest looking vertex we've ever had, but that's the way that real world problems go in general. Everything doesn't work out perfectly. So we're going to plot the point 1.5. 25/4 is 6 1/4. So I'm going to squeeze my vertex right about there. I know that the y-intercept, if I plug in 0, I get 4. So I can go ahead and put that point on there. That means that when I plug in 3, I also get 4 based on symmetry. If I plug in -1, I'm going to get -1, 0, which means based on symmetry, I'm also going to get 0 here. And let's just go one more point out. If I plug in -2, I'm going to get -4 minus 6 plus 4. So I'm going to get -6. When I connect, I'm going to have a solid curve because it's or equal to. And it says less than or equal to, so I'm going to shade below. So the solution is where these two shaded regions are overlapping, which is going to be every ordered pair in here. So hopefully you're starting to see how we can solve a quadratic inequality, a system of quadratic inequalities. Now what we're going to do is we're going to learn two last things. I know this video has a lot of different little things, but they all tie together and are also all together a great review of what we have already been doing. So let's go ahead and look at how we could solve a quadratic inequality without having to do any graphing. So here we're just going to have one quadratic inequality, and we're going to look at the solutions to this quadratic inequality, which when we graphed, we talked about there's a whole range of numbers. So wouldn't it be nice if we could list off the x values for which a quadratic inequality could be solved, the x values that make this true? Notice we don't have a function anymore. We actually have just an inequality, right? There's no y, there's no equal to. So the solution to something like this is going to be an inequality that describes all of the x values that make this true, all of the x values that I'm allowed to plug in that give me a true solution. So let's talk about how to solve this. The very first thing that you're going to do is you're going to consider how to solve this, or what this would look like if it was an equal sign. So x squared minus 3x minus 4 equals 0. You're going to solve this quadratic equality. You're going to solve this quadratic equation as if it was an equal sign. So this factors x minus 4, x plus 1. This is going to give me two solutions, and they're going to be +4 and -1. So I am going to have you graph these on a number line. These values are referred to as critical numbers. So I'm going to go ahead and put 0 in the middle, and I'm going to go by 2s just so that I don't have to write every single number. And now we're going to talk about how to interpret this solution. So if there is a less than inequality, that means our circles on our graph are going to be open, just like our dotted lines or dotted curves when we were graphing the quadratic. So I'm going to have an open circle at those two solutions that I just found. Open circle at 4, open circle at 1. Either the solution is everything in between them, or it's everything away from them, so everything that's not in between them. How you can check that is by considering a number in each of those three little sort of quadrants. And I want you to think of it as if I'm splitting this up into three different regions. You're going to test a number in each of those regions. So if I tested on the far left, I'm going to test x equals -2. And I'm going to see if that's true in our quadratic inequality, x squared minus 3x minus 4 is less than 0. If I plug in -2, I get 4 plus 6 minus 4 is less than 0. And this is not going to be true because that's not true. 6 is not less than 0. So I am not going to include that region. That region to the left of that first red line is not a part of the solution. Then I'm going to test a point in the middle area. So my favorite number to test, I can test in this middle area. I'm going to test what happens when x equals 0. That's going to be 0 minus 4 is less than 0. That's true. So I'm going to put a little check mark up here. Then I'm going to test what happens when I go to the right of 4. So I'm going to plug in something like 5. And I'm going to test what happens here. That's going to give me 25 minus 3 times 5 is 15 minus 4 is less than 0. This is not going to be a negative number, so this is not going to be true. So my solution is going to be this inequality here, which we're going to write using interval notation. Using interval notation, this inequality goes from -2 to +4, and we're using open brackets because we don't include those endpoints. Another trick that I have learned is that if it is a less than problem, it's an and problem, which means it's an interval that is connected, versus if it's a greater than problem, greater, it's an or problem, which means my graph is going to go separate ways, and I'm going to have two separate intervals that are connected. So number 7 is a greater than problem. Let's go ahead and look at that one together. So first things first, consider what would happen if this was an equal sign and go ahead and solve. So x squared plus 4x minus 32 equals 0. X plus 8, x minus 4 equals 0. So the two values that would make this equation true are 8 and -4. So I'm going to go ahead and make my number line. I'm going to go by 2's. So I'm going to put 4 here and -4 here, which means -8's over here. I'm going to put closed circles on my number line because it is a greater than or equal to. So closed circle or a filled in circle at -8 and a filled in circle at 4. So they're always going to match because they're coming from the same equation. And now I can see I need to test numbers in each of these 3 places to figure out what my solution looks like. So the first thing I'm going to test is -9. If I test -9, I'm going to get 81. Minus 4 times 9 is 36, minus 32 is greater than or equal to 0. That's going to be true. So this is going to be a part of my solution. I'm going to test in the middle. I'm going to plug in x equals 0 there. 0 plus 0 minus 32. -32 is not greater than or equal to 0. So I'm not going to include this middle area. And then I'm going to plug in a larger number for the far right, like x equals 5. If I plug that in, I get 25 plus 20 minus 32. That is going to be greater than or equal to 0. So this is going to be a part of my solution as well. So because the arrows are pointing separate ways, we're going to have 2 separate inequalities or 2 separate intervals that are our solution. So our solution is going to be from -infinity up to -8, and I'm going to have square brackets because this circle is filled in, and we're coming from forever left. Then our second interval starts at 4 and it goes forever to the right, so it's going to go up to +infinity. So the solutions to this quadratic inequality are every number between -8 down forever, and every number from 4 up forever to infinity, but not any of the numbers in between. Versus on number 6, the solutions to this quadratic inequality are every number between between -2 and +4, not including those 2 values. We will practice this more. I know this is a little tricky and a lot to think about, but we're going to wrap up this video by looking at one last type of problem, and that's writing the equation from a graph. Writing the equation of a quadratic from a graph is actually something that we have already done. The piece that we're going to add is the inequality. So remember, based on what type of information you're being given, that's going to tell you what form you're going to write it in, vertex versus intercept versus standard. So if you have the vertex and a point, like we do here, the vertex and any point, you're going to write it in vertex form. So let's actually just jump right into this problem. If we know the vertex and we know the point to negative 1, we can go ahead and write this in vertex form. So I'm going to write what vertex form is. I'm going to plug in the vertex first. The vertex is this point, so that's going to get plugged in for h and k. And then I'm going to plug this point in for x and y so that I can solve for a. So negative 1 equals a times 2 minus 5 squared plus 2. If I subtract 2 on both sides, negative 3 is going to equal negative 3 squared times a, so 9a. So a is going to equal negative 1/3. So I'm going to leave a spot for my equal sign because I need to figure out what inequality this is. But the rest of my vertex form is here. I said I was going to leave a spot, and then I wrote an equal sign anyways. So the next question I'm going to ask myself is it shaded above or below? And this graph is shaded below down here. So that means it's going to be a less than. Is it going to be less than or equal to? Well, it appears to be a solid line, so it's going to be less than or equal to. Then I can test a point like 0, 0. 0, 0 should not work when I plug it in. And that's true, it's not going to work. So this is going to be my quadratic inequality. I'm going to encourage you to pause the video and work through number 9 on your own. All right, we again have the vertex and a point. If we had the intercepts and a point, or we had 3 points, then we would take this a different way, which you can check out some previous videos to see writing equations of quadratics. So I'm going to start by just plugging in my vertex. This is going to become x plus 1 quantity squared minus 9. Then I'm going to plug in my other ordered pair, which is 3, negative 5, so 3 plus 1 squared. I'm going to add 9 to both sides, so that's going to give me 4 equals a times 16, since 3 plus 1 is 4 and I'm squaring it, which means a is going to be 4 over 16 or 1/4. So y, 1/4 times x plus 1 quantity squared minus 9. This next part is really the only part that's new. Is it shaded above or below? It's shaded above, so it should be greater than. Is it solid or dotted? It's dotted, so it should not have an or equal to symbol under it. Then we can test a point. 0, 0, if we plug it in, should be true, which in this case it is. 0 is going to be greater than 1/4 minus 9. So we know we have written the correct inequality. So to recap what we covered in this video, and I know it was a lot, we talked about how to graph a quadratic inequality, where to shade above or below, solid or dotted. We took that to an application problem. Then we talked about graphing systems of quadratic inequalities and identifying that overlapping shaded region. We talked about solving a quadratic inequality algebraically, so finding the solutions as if it was an equal sign, graphing those on a number line to figure out if it's an and or situation, and writing the interval over which our inequality, our x values, are true. And then lastly, we talked about writing the quadratic inequality from a graph. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.